Now let's apply our formulas for angular momentum for a problem. We will call it problem 2. This problem was given on one of the exams, and it says that two blocks, mass M1 and M2, are connected by a massless rigid rod. So here's the rod. It is massless and rigid. And here is block M1, and here is block M2. And this rod is attached to a vertical axle, and this axle is free to rotate. Those are important words, free to rotate. This is axle of rotation. Each mass is a distance s. This distance is s, and this distance is s. Each mass is distance s from the axle. The system is initially at rest. At time moment 0, the system is at rest. A small block of mass M3 strikes one of the blocks and sticks to it. And there is a picture provided. Now this is view from above, top view. This is M2, and this is straight line. This is M2. This is M1. This is view from above, or top view. This is axle of rotation. And I have small block of mass M3 right here, M3. It strikes one of the blocks and sticks to it. It was traveling horizontally in the plane of the board with the velocity of magnitude v1. For some reason I draw v1, but it is supposed to be v0. In the direction shown, and it is perpendicular to the rod. We ignore gravity. What will be the angular velocity of the system after this collision? So we are looking for angular velocity omega of the whole system after the collision. All right, first let's think which law will we use. This rod is free to rotate, which means that there is no friction in the bearings right here. And this means that there is no torque created by this friction in the vertical direction. So if I call this direction z, vertical direction, if tau z is 0, which means no friction, free to rotate, this means that angular z component of angular momentum is conserved. Lz initial is equal to Lz final. All we need to do, we need to figure out what is Lz initial, we need to figure out what is Lz final, and we need to solve for omega. So the system was at rest. This system was at rest. I have angular momentum, non-zero angular momentum, just because of block M3 is moving. So let's figure out what is Lz initial. Which formula will I use? I will write the formulas that we wrote in the previous video here. Definition of L. L is R cross P, or it is M R V theta, and it obeys right-hand rule. Or if I write V theta as R omega, V theta is R omega, then I get M R squared omega, right-hand rule. Or if I write it in terms of moment of inertia, it is I omega, right-hand rule. Question is, which one is good for us to describe M3? So since linear velocity v1 is given, I will just use R cross P. What will be the angular momentum of this block M3? momentum, linear momentum P is m3v1. R is from the axle to this point. But remember, we are interested, this is cross product. We are interested in perpendicular components. So which component of R is perpendicular to velocity, to P? This horizontal. So R, vector R, has this component and this component. I need to change my pen. And this component, right? Two components. So this one is anti-parallel to V1. This one is perpendicular to velocity, which means that I'm interested in this component. And I know what it is. It is S. So it is R cross P. I have P as M3V node. Component of R perpendicular to V is S. M3V node S. Now I need to check the direction. So to check the direction, we will start two vectors R and P at the same point. This is P, same direction as velocity. This is R. This is R. So from R to P. Now, since you see my mirrored image, I need to use my left hand, which is quite funny. You use your right hand. So keep left hand somewhere, use your right hand. You put your right hand with your fingers along R. It is R cross P. You cannot change the order. So first of all, even before I start doing it, let's narrow down our choices. I have cross product. Cross product is in the plane perpendicular to the plane of initial two vectors R and P. So which choices do I have? Either into the board or out of the board. So with my fingers along R, I bend them towards P. My thumb shows the direction out of the board. The direction is out of the board for the angular momentum, out, which means here, so this is top view, direction of angular momentum created by mass M3 is out. In on this picture, since it is side view, out means up. So it is up and it is LZ. We are right. It is positive LZ component of angular momentum. Initial angular momentum created by M3 is just M3V node S. Great. Everything else is at rest. Now what is LZ final? Now I need LZ final. If I write here, will you see it? LZ final. LZ final, now this M3 strikes M1, sticks to it, and now they are moving together. So I have M1 plus M3 after the collision. Let me bring M3 here now. So what happens after the collision? Now I have M1 plus M3 moving together. So M3 strikes M1 and then system starts spinning about this axle. What is LZ final? Let's figure out which formula to use. We are looking for omega. So I will be using formula mr squared omega. What do we have? We have M1 plus M3. R is S squared, omega. And I have M2 also rotating, plus M2 S squared omega. How do I know that it is plus? It's rigid rod, so they are spinning in the same direction. Again, I have positive Z projection of angular momentum. Now I'm ready to put this to equal LZ initial, M3 V node S, is equal to LZ final. I will factor out omega. Can I do it? Actually, I can also factor out S squared. It will be M1 plus M2 plus M3 and then S squared omega. S squared omega. Look, I have one equation, one unknown variable, which is omega. We can solve the problem. What is omega? It is M3 divided by M1 plus M2 plus M3. S and S cancel out. And then I have M3 this, and then I have V naught divided by S. What do we miss? We miss the direction. What will be the direction of rotation? When we indicate the direction of omega, we usually put clockwise or counterclockwise. So if I look from the top, what will be the direction of rotation? Oh, I need to, you see my mirrored image. I need to remember this. So I follow the rotation, and the rotation is counterclockwise. Counterclockwise direction. So we found omega. Problem solved. Now, what I want to emphasize here, some students make mistake right here. So they, for some reason, they put S squared. No, what we used here was linear velocity. So it is R cross P. It is M from P, velocity from P, from momentum, and then R, mr v theta. There is no R squared. Otherwise, dimension will be wrong. And only when you express linear velocity in terms of angular velocity, you write v theta as r omega. That's when you get R squared. That's why when we express it in terms of angular velocity, it is S squared. Now, how this problem will be changed if I add that the rod is not massless. It now has a moment of inertia that is given. So let it be given. Moment of inertia of the rod is I naught, about the center. Moment of inertia has to be provided about the axle, some axle of rotation. So I naught, moment of inertia of this rod about this axle, is given. How this equation will be changed? Well, the initial angular momentum is still m3 v naught s. No changes. This system is at rest. Then it is equal to m1 plus m2 plus m3. No changes here. S squared omega plus, now I have to use this formula, moment of inertia of the rod, since it's not massless anymore, times omega. So you factor out omega from the right-hand side, and you solve this equation. What will be omega? In this case, omega will be, I'll write long line. It will be m3 v naught s divided by m1 plus m2 plus m3 s squared plus moment of inertia I naught. Okay, I just realized, first I forgot to add the direction here. Of course, it is again counterclockwise. Counterclockwise. I also realized that at the very beginning, for some reason, I switched V1 to V naught. Remember, when I draw the top view, here is M2, here is M1, and here is M3 moving. I draw V1, but it is supposed to be V naught. And now everything is correct. The initial angular momentum of M3 was M3 V naught